Hello friends and my dear students, as you can see we are studying this third year 6th semester BTECH mechanical engineering curriculum, in which we are studying the subject of mechanical vibration, which is under the Rajasthan Technical University quota curriculum. So as you can see that we have already covered these topics, unit 2, what are the objective and scope of this particular course. Then we started with the introduction of sound, which we covered with, followed by introduction of noise, then introduction to vibration we have studied in unit 2. Then undamped vibration, okay, means natural vibration or free vibration we have studied. Then damped vibration we have studied, and as well as we have also studied the vibration characteristics of Coulomb damped system. Even we have also covered few numerical related to this particular unit number 3 as well. Okay, so you can go through those particular videos in the previous recorded sessions of this particular subject. So we are going to start this force vibration. Okay, so and this is followed with, if you will understand this properly, then only you can be able to understand the system with 2-degree vibration system and multi-degree vibration system, which are the consecutive units of this particular subject. Okay, so we'll start with the force vibration of single degree freedom system, and let's see that how you can calculate the frequency response curves and phase angle plots, as well as we will also see that vibration isolation and transmissibility factors and their proportions. Okay, and what are the force vibration with the rotating and reciprocating unbalance, and what are the materials which are going to be used for vibration isolation. So these are the topics which we are going to cover in this particular unit. So let's get it started. As you know that force damped vibrations are the perfect reality of any kind of vibrating or vibration system, because here you will observe that there will be some kind of unbalanced force. As you can see in the picture, this is your spring, this is your damper, and this is the mass, and at the end of the mass means at the mass you are applying some kind of unbalanced force, which is of the magnitude of f naught sine omega t. Okay, where omega is the frequency of the force. Okay, so this is the Fn or F unbalance. Now if you will apply the D'Alembert's principle, then your free body diagram will look like this: Sx Cx dot plus Mx double dot in the upward direction, while this rotating unbalance, or you can say any kind of unbalance which is there, here we are just taking it as a rotating unbalance, which will come in the picture. Okay, and this is come because of the unbalanced forces. So if you have recall your unbalanced theory of rotating unbalances and reciprocating unbalance, which you have studied in the previous syllabus of DME1. So if you recall those chapters, then you can see that this is a kind of unbalance in any kind of rotating machinery of mechanical component. So this unbalanced force is m chuck, or whatever the mass of the chuck, into e omega square into sine omega t is coming from chuck, but the lathe machine will suffer because the vibration. So we have to deal with the vibration in the lathe machine as a system, and mass m is the mass of a lathe machine, where mass is this chuck should be there for the unbalanced force, but here total mass, this total mass will be of the mass of the lathe machine, which we have to encounter here. Okay, now let's see that if you are having these two unbalanced forces or two vibrations, let omega n square minus omega square, that we will see this calculation for, how it will come like this. Okay, so according to the D'Alembert principle, your equation will be like this: mx double dot plus cx dot plus sx minus f naught omega sine omega t. If you will equate this equation, then it will be look like this, and this is also, this is with the help of mathematical equations, your final solution will be CF complementary function plus particular integral, if you will equate, because CF x, okay, it will tends to 0 after some time when zeta is greater than 1 or equal to 1. These are the three conditions, and pi will be same for all the cases. Okay, so pi you can calculate it like this, which is your f naught by m sine omega t, okay, divided by d square plus 2 zeta d square plus 2 zeta sine omega t d omega n d plus omega n square. And if you will rearrange this particular formula, then you will get pi as f naught by s and divided by under root 1 minus omega by omega n square whole square plus 2 zeta omega by omega n whole square into sine omega t minus phi. Do practice that how it will come like this. Apply the mathematical principle of solving the differential equation, and this pi will be never be 0. And this is this whole blue color circle bracket magnitude is amplitude, and it dependent on time, that's why it is constant. And this is sine or harmonic wave will be generated because of this particular sine function in the formula. So this is kind of vibration. So in force damped vibration, this will never stop, or this will be a continuous, it will continue for a longer duration or longer time. It will not stop, or force time vibration will not be equals to 0. Now, as vibration is running, system will never stop. So means CF, at some time CF and PI will be there, and after some time that PI will be continuous, and you will feel a constant vibration. So every mechanical system having a running life. That's why, because of this particular thing, that every kind of mechanicals, either rotating or non-rotating or reciprocating system, have some kind of mechanical life. Okay, some kind of life will be there. So in this way I'm stopping here. I will continue with the same thing in the upcoming sessions, okay, in the topic of force vibration. So stay tuned with the Engineering College Banswara YouTube channel for more such updates about different branches of engineering like mechanical, electrical, civil and computer science engineering. If you have any doubt, do comment on the at the comment box of this particular video, and thank you so much for your patience hearing. Thank you so much.